Differential geometry plays a critical role in modeling the state before the Big Bang, providing the mathematical foundation needed to understand the curvature of spacetime and the dynamics of the universe. This branch of mathematics focuses on the properties and applications of geometric structures, allowing scientists to express complex ideas about the fabric of spacetime in a precise and rigorous way. In cosmology, differential geometry helps describe how the universe can curve and bend, which ultimately leads to various theoretical models of its origin, including those that assume a pre-Big Bang state. In the context of the general theory of relativity, which describes gravity as the curvature of spacetime, differential geometry allows researchers to formulate equations that define how matter and energy affect the geometry of the universe. These equations can show how spacetime behaves under various conditions, including high-density states that may have existed before the Big Bang. Thus, the use of differential geometry allows for a deeper understanding of singularities, points in spacetime where the gravitational field becomes infinitely strong, as well as areas where traditional physics breaks down completely. Moreover, differential geometry facilitates the study of exotic theories about the origin of the universe, such as string theory and loop quantum gravity. These models often rely on complex geometric structures that describe extra dimensions or quantum properties of spacetime. Using differential geometry, scientists can analyze how these structures might interact or evolve, providing insights into possible pre-Big Bang scenarios that challenge traditional notions of time and space. Ultimately, the mathematics of differential geometry enriches our understanding of the genesis of the universe and the conditions that may have prevailed just before the Big Bang. It brings together abstract mathematical concepts and physical theories, allowing a comprehensive exploration of the relationships between space, time, geometry, and the fundamental forces of nature. This interplay between mathematics and physics is crucial for advancing our knowledge of the earliest moments of the cosmos and potential states that existed long before our current view of the universe was formed. Topology plays an important role in describing conditions prior to the origin of the universe, offering a framework for understanding properties of space that remain invariant under continuous transformations. In the context of cosmology and theories related to the pre-Big Bang state, topology helps analyze the fundamental structure of the universe and its potential geometric configurations. By investigating topological features of spacetime, physicists can study different scenarios for the origin and evolution of the universe. One of the most important aspects of topology is its ability to classify spaces based on their connectivity and dimensionality. In a pre-Big Bang context, researchers could study how different topological structures could give rise to different kinds of universes. For example, the idea of a universe with a non-trivial topology, such as a toroidal shape, can influence particle trajectories and the overall geometry of spacetime, affecting how the universe expands and evolves. Understanding these topological configurations provides insight into the fundamental characteristics of the early universe and informs models that attempt to describe its behavior. In addition, topology allows for the exploration of concepts such as wormholes and other exotic structures that can facilitate connections between different regions of spacetime or even different universes. Such ideas remain speculative, but they are worth considering when studying the conditions preceding the emergence of the universe. By analyzing the topological properties of these hypothetical structures, scientists can explore implications for causality, the flow of time, and the possibility of quantum effects that could affect our understanding of both the Big Bang and what came before it. In addition, topological concepts help distinguish between different phases of the evolution of the universe. Topological transitions can occur when the universe undergoes phase changes, such as changes in symmetry or vacuum states, which can affect the fundamental forces and particles that characterize the cosmos. By studying these transitions in relation to conditions prior to the Big Bang, researchers can develop models that allow for a more nuanced understanding of the early states of the universe and the variety of pathways that may have led to the universe as we know it today. Overall, topology serves as a vital tool for expanding our understanding of conditions prior to the emergence of the universe and their implications for the fundamental nature of reality. Quantum field theory plays a key role in the study of the origin of the universe because it provides a framework that combines quantum mechanics and special relativity, allowing physicists to understand fundamental particles and their interactions in the early universe. This theoretical approach is essential for studying phenomena that occurred immediately after the Big Bang. Quantum field theory allows researchers to study the behavior of particles and fields at extremely high energies and densities. The application of quantum field theory to cosmology leads to significant discoveries regarding the conditions and dynamics of the origin of the universe. One of the major contributions of quantum field theory to our understanding of the origin of the universe is its ability to describe the behavior of fundamental particles as excitations of underlying fields. In the early universe, when temperatures were unusually high, all known particles existed in a high-energy state, and quantum fluctuations played a crucial role in shaping their interactions. Using quantum field theory, scientists can model these fluctuations and establish how they contributed to the initial conditions necessary for the expansion of the universe. In addition, quantum field theory introduces concepts such as vacuum energy and spontaneous symmetry breaking, which are extremely important when considering the early universe. For example, the mechanisms proposed by inflationary models, the rapid exponential expansion of space during the formation of the universe, rely on quantum field theory to describe how a scalar field, often called the inflaton field, can drive this expansion. Understanding how vacuum energy associated with quantum fluctuations can lead to inflation provides insight into the very rapid growth of the universe, fundamentally altering its future evolution and structure. In addition, quantum field theory allows researchers to study the interaction between different fields in the earliest moments of the cosmos. The interactions between different forces, such as electromagnetism, weak nuclear forces, and gravity, can be studied through the lens of quantum field theory. This allows physicists to investigate the unification of forces at high energies and explore how they may have acted in a unified fashion in the early universe, which informs models that attempt to understand the transition from this primordial state to the diverse structure we see today. To summarize, applying quantum field theory to the study of the origin of the universe provides powerful tools for understanding the fundamental processes that have shaped the cosmos. This allows scientists to study the dynamics of particle interactions in high-energy environments, explore the consequences of inflationary scenarios, and establish links between the fundamental forces that govern the evolution of the universe, ultimately improving our understanding of how the universe came into being. To model the transition from pre-Big Bang to Big Bang states, physicists and mathematicians use a number of advanced mathematical tools and frameworks. These tools facilitate the study of the complex phenomena occurring at this crucial juncture in the history of the universe by combining concepts from different areas of mathematics and theoretical physics. One of the basic mathematical foundations is differential geometry, which helps describe the curvature of spacetime. This is important for understanding how gravitational forces affect the behavior of matter and energy in the context of the expansion of the universe. Einstein's field equations, which underlie the general theory of relativity, are formulated within this theory, allowing researchers to study the dynamics of spacetime as it evolves from a singularity or high-density state to the expanding universe we observe today. Another important tool is dynamical systems theory, which studies how systems evolve over time. This area of mathematics is particularly relevant in studying the stability and instability of cosmological models. By applying dynamical systems theory, scientists can analyze how small fluctuations in the state of the universe can lead to dramatic changes, as is the case in models emphasizing phase transitions or the dynamics of inflationary scenarios. This approach helps us understand how the universe can transition from pre-Big Bang conditions to the high-energy state characteristic of the Big Bang. In addition, the mathematical tools of quantum field theory play a key role in studying the fundamental particle interactions that can determine this transition. Methods such as perturbation theory and the path integral formulation are crucial for studying the behavior of quantum fields and their fluctuations in the early universe. These methods allow physicists to model quantum processes, such as vacuum fluctuations, and their contribution to the conditions that led to the rapid expansion of the universe. Finally, topology also provides valuable insight into the transitions that can occur in the universe. Studying topological properties can help in understanding the nature of phase transitions that can occur as the universe expands and cools, affecting how different forces and fields interact and manifest themselves in the observable universe. By integrating these mathematical tools, researchers will be able to build comprehensive models that capture the complexity of the transition from pre-Big Bang states to Big Bang dynamical processes, improving our understanding of the origin and evolution of the universe. Non-commutative geometry arose from the attempt to describe the fabric of spacetime on extremely small scales, especially in the context of quantum mechanics and general relativity theory. At these levels, traditional notions of geometry based on smooth manifolds may not be adequate. Non-commutative geometry provides a framework in which spaces are defined by algebraic structures rather than points. This concept has profound implications for understanding the early universe, especially the moments immediately following the Big Bang. In those initial moments, the universe was incredibly dense and hot, with energies high enough to allow ordinary geometry to collapse. Here, non-commutative geometry assumes that spacetime itself may have a fuzzy quality, where the very position of points is indeterminate. This approximation to space leads to the idea that distances and spatial separations are not well defined. Instead, they are affected by quantum uncertainties, which is consistent with the principles of quantum field theory. The use of non-commutative geometry allows physicists to investigate the behavior of various fundamental forces under these extreme conditions. This provides elegant scenarios for unifying quantum mechanics with gravity by revising our understanding of scales and interactions. In addition, this geometric perspective has spurred theoretical frameworks such as string theory, where non-commutative properties may be important for reconciling gravity with other forces in nature. Researchers are also using non-commutative geometry to analyze the evolution of forces and particles after the Big Bang, contributing to models that explain cosmic phenomena, such as inflation and galaxy distribution. These theories can provide insights into the cosmic microwave background, radiation, and gravitational waves, helping us explore the early history of the universe and its fundamental nature beyond what classical physics predicts. Group theory plays a critical role in understanding symmetries in physics before the Big Bang, providing a mathematical framework for describing the behavior of physical systems under transformations. At a fundamental level, symmetries can reveal constants of nature and help us form theories about the early universe. In the context of the pre-Big Bang scenario, where classical notions of time and space become blurred, group theory helps physicists explore the relationships between different forces and the particles that embody them. One of the central tenets of group theory is that to every symmetry there corresponds a conservation law. For example, when a system has rotational symmetry, it means that angular momentum is conserved. The principle extends to a variety of interactions in the universe, including those that govern the fundamental forces. By applying group theory to the early universe, Scientists are exploring symmetries related to particle interactions and their importance in shaping structure and evolution before the Big Bang. In particular, in models of the universe before the Big Bang, such as the ekpyrotic or cyclic theories of the universe, group symmetries help formulate the behavior of spacetime and energy in their complex interactions. For example, transformations characterized by these groups can lead to mechanisms governing cosmic potentials and scenarios without singularities. Thus, the exchange between particles mediated by these symmetries can hint at the paths the universe may have taken to get to its current state. In addition, understanding these symmetries can help physicists build models that unify quantum mechanics and general relativity. Using group theory, scientists can investigate the unification of forces and ultimately contribute to a broader understanding of the conditions that may have existed before the Big Bang, as well as the nature of the structure of the universe at its very core. Mathematical modeling of the concept of infinite density in the Big Bang singularity involves the application of the general theory of relativity and the equations governing the behavior of the universe. When physicists investigate singularities, they face the limitations of our current scientific framework, where the equations of the general theory of relativity begin to break down under extreme conditions. A typical model to describe the early universe uses the Friedmann-Lemaitre-Robertson-Walker metric, which expresses a homogeneous and isotropic universe. If we rewind time back to the moment of the Big Bang, the models suggest that as the universe shrinks, all matter and energy is concentrated into an infinitesimal point. This leads to what we call a singularity, where density is considered to be infinitely high. In mathematical terms, this means that when attempting to calculate density by dividing mass by volume, both approaches result in violating the equations. Thus, instead of yielding meaningful values, the equations yield infinities, signaling that our understanding of physics has reached an impasse. In addition, physicists utilize the concepts of quantum mechanics, leading to the creation of theories that extend classical general relativity to the quantum realm. Models based on loop quantum gravity assume that spacetime itself can be quantized, with no real singularity existing because it inherently avoids infinite density. Instead, these models assume the existence of a minimum length scale, which provides a new way of looking at the density and structure of spacetime at the time of the Big Bang. Therefore, while conventional math predicts infinite density leading to singularities, more advanced theories aim to provide a framework that can account for the dynamics occurring at these extreme states. By integrating the ideas of general relativity theory and quantum mechanics, scientists continue to explore the nature of the universe at its origins, exploring models that may eventually lead to a coherent description of the conditions that existed at the time of creation. Reconciling quantum mechanics and general relativity, especially in the early universe, is one of the most important challenges of modern theoretical physics. Several mathematical schemes are used to consider this complex interaction, each of which makes a unique contribution to understanding the conditions that prevailed shortly after the Big Bang. One of the best-known models is string theory, which posits that fundamental particles are not point-like, but are one-dimensional strings. This approach inherently incorporates both quantum mechanics and general relativity, requiring the integration of all forces in a higher dimensional space. String theory leads to a myriad of mathematical interpretations and structures, including the concept of extra dimensions that can help explain phenomena such as gravity and combine it with electromagnetism and nuclear forces. These higher dimensions allow for a rich tapestry of potential interactions and offer possible solutions to the problem of singularities. Another important concept is loop quantum gravity, which attempts to quantize spacetime itself. Unlike string theory, it does not rely on higher dimensions, but treats space and time as discrete entities that can be represented by quantized loops. This model assumes that on very small scales, space-time behaves as a network of interconnected loops, eliminating the singularity characteristic of the classical general theory of relativity. By describing gravity in quantum terms, loop quantum gravity provides an alternative view of the early universe that avoids infinite quantities. Quantum field theory also plays a crucial role in these reconciliation efforts. By developing a quantum version of gravity, physicists seek to formulate a self-consistent theory that incorporates gravitational effects into the framework of quantum mechanics. Approaches such as effective field theories explore the low-energy limits of quantum gravity, allowing us to predict events in the early universe, such as cosmic inflation and particle formation in a rapidly expanding cosmos. By exploring these concepts, physicists seek to achieve a comprehensive understanding of the origin of the universe, moving toward a unified theory that could elegantly combine the principles of quantum mechanics with the geometric insights of general relativity. Each approach offers valuable perspectives, contributing to the ongoing quest to decipher the mysteries of the cosmos. Applying information theory concepts to pre-Big Bang models provides new insights into the evolution of the universe prior to its expansion. Information theory offers valuable tools for understanding how information is stored, transmitted, and processed in physical systems, which can be particularly useful in analyzing early configurations of the state of the cosmos. This approach shifts the focus from simply describing the universe in terms of matter and energy to considering the fundamental nature of information itself as a determinant of cosmic events. One of the most important concepts in information theory is entropy, which refers to the amount of disorder or uncertainty in a system. In the context of the early universe, researchers are studying the behavior of entropy in the conditions preceding the Big Bang. Some pre-Big Bang models suggest that the conditions of the universe were determined by high entropy states, leading to the emergence of a homogeneous and isotropic universe from a more complex and entangled information structure. Understanding entropy allows physicists to analyze how the transition from a high entropy state to a low entropy state, as observed in the expansion of the universe, affects the formation of structures such as galaxies. Moreover, in systems such as loop quantum gravity, information theory can be used to describe how quantum states transform as the universe evolves. It assumes that the information content of the universe is conserved and fundamentally related to the geometry of spacetime. By interpreting the fundamental laws of physics as algorithms for information processing, scientists can explore how quantum fluctuations may have affected the transition from the pre-Big Bang state to the observable universe, focusing on how quantum states encode information about underlying structures. Finally, applying information theory to general cosmological models allows us to understand how the laws of physics can emerge from more fundamental informational principles. Ideas such as holographic principles show that the three-dimensional information of the universe can be encoded on a two-dimensional surface. This concept not only deepens our understanding of gravity and quantum mechanics, but also suggests that the fabric of the universe is intricately woven from threads of information, allowing physicists to hypothesize about the behavior and evolution of the universe all the way back to the Big Bang. Chaos theory plays an interesting role in understanding the emergence of our universe, allowing us to understand how complex systems evolve from initial conditions that may appear simple or homogeneous. At the heart of chaos theory is the idea that small changes in initial conditions can lead to very different outcomes, a concept often referred to as the butterfly effect. This principle may be of great importance when applied to the early universe, where countless variables interacted under extreme conditions. In the context of cosmology, the dynamics of the universe in the moments after the Big Bang can be viewed as a chaotic system. The initial state of the universe, characterized by high temperatures and densities, set in motion a number of processes that were very sensitive to their conditions. As the universe expanded and cooled, small fluctuations in density led to the formation of galaxies, stars, and larger cosmic structures. Understanding these processes through chaos theory allows scientists to model how diverse and intricate patterns can emerge from what might initially appear homogeneous. In addition, chaos theory contributes to the study of cosmic inflation, the rapid expansion of space that occurred shortly after the Big Bang. The inflationary scheme suggests that quantum fluctuations during this period can generate density variations that are necessary for the large-scale structure of our universe. In this sense, chaotic dynamics can help describe how these fluctuations evolve and affect the distribution of matter. Thus, chaos theory not only clarifies the behavior of systems in the early universe, but also helps theorists understand how randomness can lead to the order observed in cosmic structures today. In addition, researchers are increasingly exploring the connections between chaos theory and quantum mechanics, providing a deeper understanding of how quantum uncertainties can contribute to chaotic behavior at cosmic scales. This intersection emphasizes the complexity of the universe's evolution and suggests that reliable structural models can emerge against a backdrop of apparent randomness. Through the lens of chaos theory, the emergence of our universe becomes a story of unpredictable interactions and complex behavior, emphasizing both the intricate nature of cosmic evolution and the subtle laws that govern it.